Hello, welcome to this video on gravitation, a plain language deep dive. Gravity is the universal attraction between things with mass. It acts everywhere and all the time. If you jump up, you're going to come down. That's gravity. You're technically attracted to the chair you're sitting on, gravitationally speaking. But of course, we're all most attracted to the Earth, because the Earth is the most massive object near us. So the law of gravitation, in words, is simply that every object pulls on every other object. The pull gets stronger if the objects are more massive, and gets weaker when the objects are further apart. That weaker with distance part follows an inverse square law. You double the distance, the pull is about 1/4 as strong. So the force of gravity is inversely proportional to the square of the distance. So you double the distance, the pull is about 1/4 as strong. You triple the distance, it's about 1/9 of the strength. That's the heart of the inverse square idea. This idea will come back in future videos because this relationship is very important in nature. Why inverse square? Well, picture the pull spreading in all directions. As distance grows, it spreads over a much larger sphere around the source. Spheres get bigger fast. Their area grows with the square of a distance. Right? Remember, the area of a sphere is equal to 4 pi r squared. So if you double the radius of a sphere, you're increasing the area by 4. If you triple the radius of a sphere, you're increasing it by 9. So the same amount of influence is thinner and thinner far away. Fundamentally, this is a big reason why the inverse square law appears everywhere. Because a lot of stuff propagates through all of space, kind of like a sphere in all directions. So mass is just how much stuff there is. It doesn't change when you move. The mass that you have here on Earth is the same as the mass that you would have on the moon or in Mars. But weight is how hard gravity pulls on that mass. It can change with location. Your weight on the moon is not the same weight that you have on Earth, simply because the moon is a fraction of the mass of the Earth, and hence about 1/6. The mass isn't 1/6, but the gravitational pull on you would be about 1/6 of the weight that you have here on Earth. So mass is not equal to weight. Mass is invariant, meaning that it doesn't change, doesn't depend on location, whereas weight depends on the gravity of where you are. Now, gravitational field, or just a field, is a way to describe how strong a pull is at each place. You can imagine a map where every point has a little arrow showing the pull. Everyday consequences, without math and just building intuition. Near Earth's surface, the pull barely changes as you climb a building because Earth is enormous compared to that height. Everything falls the same in a vacuum. A hammer and a feather drop together if there's no air resistance. I encourage all of you to look up a YouTube video where you can see this for yourselves. When something falls, gravity turns stored energy into motion. Energy doesn't appear or vanish, it changes form. Orbits are basically objects or trajectories where something is falling without ever hitting the ground. So a satellite is constantly falling, but moving sideways fast enough that the ground curves away beneath it. Planets orbit the sun for the same reason. The inverse square law says pull provides the exact tug needed to keep them curving. Tides? Well, that's gravity's difference across distances. You see, the moon pulls a little harder on the side of the earth closest to it, and a little weaker on the far side. The difference stretches the oceans into two bulges, giving us two high tides most of the day. So why do we have tides? Well, you can thank gravity, the moon's gravity. The moon's gravity pulls on the Earth's ocean about twice as strong as the sun. But both the moon and the sun impact tides. And hence we get different kinds of tides, depending on the orientation of the moon and the sun with respect to the Earth. Everywhere in nature are examples of the inverse square. Light brightness. A flashlight looks 4 times dimmer at twice the distance because the light spreads over a sphere. That's 4 times the area. Sound intensity. Music fades fast as you step back, roughly quartering at double distance when there's no echoing or walls. Radio and Wi-Fi. Signal strength drops steeply with distance in open air, before walls, antennas, and interference complicates things even further. The electric force between charges follows the inverse square law too. Same geometry. Influence spreads out bigger and bigger surfaces, over bigger and bigger surfaces. Gravity itself is the classic example governing orbits, tides, and even the structure of galaxies. We, the Earth, orbits around the sun. The sun is actually orbiting around the center of the Milky Way, where there is a giant black hole, massive giant black hole. When the inverse square idea doesn't quite hold, well, if something absorbs or blocks a signal, for example, if you have fog and light, or if you have walls for sound, it can fade even faster than the inverse square. If you focus energy, a lens, a dish, a megaphone, you can make it drop off slower in the favored direction. Close to a complicated source or very near field, patterns can be messy before they settle into the simple, spread out picture. How? We know this story is right. Again, it always comes back to evidence. Planet motions match the inverse square pull with precision. Ellipses, positions, and spacecraft's paths all check out. On Earth, sensitive torsion balance experiments directly measure the tiny pull between masses, confirming the law. Modern space missions use gravity maps of planets and moons to navigate and to measure hidden features like mountain roots and massive lumps. If gravity had a catchphrase, it'd be spread the love, thin it with distance. Quick recap. Gravity is a universal pull that gets stronger with mass and weaker with distance, following an inverse square rule. So I should actually put mass here. The inverse square law shows up in light, sound, radio, electric force, and gravity, because influence spreads over bigger spheres as you move further away. Orbits are free fall around a curved world. Tides come from small differences in the moon's pull across Earth. And experiments from the lab to deep space confirm this picture again and again. Thank you for joining me today, and I hope you enjoyed the video.